Dear friends, students and learners, I am Dr. Shashank Shrivastava from the School of Engineering Technology in the Gandhi National Open University. So as you know, I am bringing before you the material science course offered by the university. So today I am putting forth before you module 9 of the course of material science. So we start now. So in this session we will discuss about time temperature transformation first of all. So why do we need the time temperature transformation? So we see that information from the phase diagram of iron carbon system is useful actually for increasing the strength and eliminating locked in stresses by retaining or avoiding a particular phase. So in that iron carbon diagram we studied about the different phases like the austenite and the ferrite and the perlite and various other phases, cementite. So all these we studied about, and we found out how by varying carbon percentage different things we are getting, and by different cooling rates also we are getting different kinds of steels. So all these things we saw in the iron carbon diagram. Now why we are using the time temperature transformation diagram? So the main drawback of the iron carbon phase diagram was that it represents only the equilibrium cooling. That means we are considering the phase changes in the equilibrium position, meaning they are going very slowly. The cooling rate is almost supposed to be constant, but in reality the cooling rate varies. So accordingly things will also vary, and we will get different combinations of steels. So for that purpose we have the time temperature transformation diagram. Like we know that equilibrium cooling is neither obtained in practical sense and nor it is conducive to develop desired strength and structure in a particular steel. Increasing cooling rates reduces the transformation temperature as was highlighted and may result in formation of the metastable phase. So there are different things which can happen. It's not always equilibrium condition. So we need the TTT diagram, time temperature transformation diagram. So some examples of the drawbacks in the iron carbon diagram are given here so that you can understand it better. Suppose there is a very high cooling rate of iron carbon system in a steel range, then it causes development of a metastable phase called martensite. So that martensite was not shown in the iron carbon phase diagram. So that was one drawback. The second is the steel and cast iron normally carry some alloying elements, though in very varying amounts. These alloying elements have great deal of influence on precipitation of all the phases. So these changes were not represented by the phase diagram. So now we come to the time transformation diagram. How it is obtained, how it is experimentally determined. So a number of samples of the size of say small coins, like we have 50 paisa and all those coins, 1 rupee coins, so they can be used, and they are austenized. Austenite is a part of that diagram, so they are austenized just above the temperature of 723 degrees centigrade. And what was that temperature? Like we discussed in the last time, it was the eutectoid temperature. So then the samples after going up to this temperature, they are rapidly cooled in a salt bath which is maintained at a temperature slightly below 723 degrees centigrade. So salt bath is a kind of a furnace. After allowing various time intervals, the specimens are taken out one by one from the salt bath and quenched into water at room temperature. So they are taken out, the specimens, one by one, and further quenched into water at the room temperature. And this experiment is repeated with isothermal transformation of eutectoid steel. Both types, hypo and hyper eutectoid steel, at progressively reducing temperatures. So here we see the diagram. If temperature of the transformation is plotted as a function of time of transformation, then the resulting schematic curve is known as the time temperature transformation diagram, and you can see it in this figure. So here you see temperature is on the y-axis and time is on the x-axis, and the starting of the transformation is given by the line which is marked as PS, which is shown here by the red arrow, and the finishing of the transformation is given by the line that is marked as PF, and that is shown here by the green arrow. So you can see here, when we start, suppose we are starting at one point, then in the beginning what happens, that the transformation rate starts at a certain point which is very slow, meaning the rate of transformation is very slow. So it is at a larger distance from the y-axis or the temperature axis, if you see at the top of the figure. And then there is certain time of transformation after which it gets transformed. So there is a gap. It has started at certain point, you can mark it on the graph, then after a certain time it will finish. So you can mark this second point also. So as you come down in the graph, you will see that the time of transformation, the start point actually will be getting closer to the y-axis, that is the temperature axis. Why it is happening? Because the cooling rate or the rate of transformation is increasing. So the start point gets closer to the temperature axis, and similarly the finish point also. So like that we can mark these points and we can come down, and you will see there will be a bend. Why this bend or the neck is coming? Because that is the point of the maximum rate of cooling. That means that the transformation starts at an early point and it also finishes earlier. So this is the point, and here is the neck, you can see in the diagram. And further after this, graph will again move forward from the bend. So this is the whole scenario. There will be a neck in the graph, and in the beginning the time transformation diagram will start at a later time, and towards the end also it will start at a later time, but in the middle it starts earlier. That's why the neck comes in. So now we see that this coarse pear light is formed in the beginning, and finally when we move down in the graph, then we can see then fine pear light is coming in, and further bainite is also there. So these are the two figures you can see, A and B, and the first one is about 0.8% carbon is steel, and the second one is about the 0.3% carbon is steel. So these two figures are there. In the first one you see, because it is 0.8%, it is slightly at a larger distance from the temperature axis in comparison to the figure B. It is touching with the temperature axis, the B1, you can see, because the carbon content is lesser there. Then one more thing you can see, I have represented this distance between the finish and the start by E and F at the beginning of the transformation, and by C and D at the neck point. So see the difference between EF and CD. E is at a farther distance from the temperature axis, whereas C is at a much lesser distance from the temperature axis, and that is because of that only, because the temperature is going down quickly, so the cooling rate is higher. And different steel varieties that we are getting are given here. Like I told you earlier, near the 723 degree temperature range, towards the right of this time transformation diagram, you can see there is coarse pearlite. Towards the neck it is the fine pearlite, and at the bottom towards the right part of the time transformation graph there is bainite. And further at the bottom there is one more thing, that is martensite. So how this martensite is formed is that if the rate of cooling is very high, so it will not go into this transformation thing, and it will bypass that. It will not cut the neck anywhere and simply come down to martensite. So this is about the two graphs and with different compositions of carbon. So in the figure B which I showed you earlier, this was the neck was touching the temperature axis. So here you can see one more thing, that even the fastest cooling rate if we give the fastest cooling rate, it will not be able to meet the nose of the S curve. The nose and this line representing fastest cooling, suppose that is vertical line, it will just be tangent to the nose, it will not cut it anywhere. Hence 100% martensite will not be retained at room temperature in this structure of the steel. The important feature of the TTT curve is its bending backwards at nose. Below the nose, the austenite transforms into bayanite, as I told you earlier. Whether it is perlite or bayanite at a temperature called MS, MS is the start of the martensite. The transformation into a transition phase martensite takes place. So martensite also has a start point and a finish point. So as soon as the temperature reaches MS, martensite formation will take place. Both bayanite and martensite may be retained in a steel by controlling the rate of cooling. So it all depends on the rate of cooling. Suppose we give a certain rate of cooling where it doesn't form martensite completely, so there will be a mixture. Bayanite and martensite both will be there. If cooling is sufficiently fast so that nose is avoided, then austenite transforms into bayanite. If the part is now held at this temperature for sufficiently long time, the bayanite is stabilized. So that way the bayanite is formed. That the nose is also avoided, but we are not getting completely the martensite. So bayanite will be there and it will also be stabilized if we are holding it at that temperature for sufficiently long time. Unlike perlite, in bayanite the cementite is in particle form, distributed uniformly in the matrix of ferrite. Like I had told you in previously also, that perlite is in the form of layers. Layers are there. But in bayanite, there are no layers, it is in particle form. Bayanite is harder, stronger and tougher than perlite. Obviously, when it will be in particle form, so it will be more compact and these particles will be together and without any space or interstitial space. So it will be much tougher and stronger. Bayanitic steel is more ductile than perlitic steel for some level of hardness. That is also the case. If heated steel is cooled sufficiently fast beyond the nose, then at MS temperature martensite is formed. So earlier we saw that bayanite is formed if it is cooled somewhat near the nose of the curve, but if this steel is now cooled at a much more rapid pace than the previous one, then it will go much beyond the nose, and at MS temperature only martensite will be formed. So this transformation is complete at a temperature MF. So start of martensite is at MS and completion is at MF. Martensite has carbon dissolved in iron, whereby its BCC structure changes into body-centered tetragonal structure. So what happens here? First of all, there is the BCC structure, body-centered cubic, where this carbon atom is in the center of the cube. But this martensite, what happens in martensite, this carbon atom tends to elongate the edge because it wants to get into the edge of this particular structure between two iron atoms. So then it causes distortion. So now the whole structure doesn't remain BCC anymore or cubic anymore, it becomes tetragonal instead, with one of the sides longer or shorter than the others. So that's why it is known as body-centered tetragonal structure. Martensite is marked by high hardness because of the distortion, as I told you, of the iron lattice. Then very fine size of the martensite plates, since the plates are very fine and small in size, so hardness is very good. And also because of the high density of dislocations associated with twinning. So twinning also happens here. So this figure, if you can see, this schematically shows the cooling pattern to produce different phases in steel. So it is the TTT curve for steel with different cooling rates. So the cooling rates, if you can see in the figure, they are given by the dotted lines. So is the first dotted line, which is much beyond the nose of the curve, then the second one is just tangent to the curve, and then the third one is crossing the curve much towards the righter side of the nose, and then the fourth one is much beyond the nose towards the righter side of the curve. So heat treatments given to steel will be governed by the cooling rates producing final phases with pearlite, bainite or martensite. So depending upon this cooling rate, different kinds of steel will be formed, and out of those the most commonly known are the pearlite, bainite and the martensite. So we can see here that many refinements are possible with control of cooling rate and soaking time. So we now will see the formation and characteristics of the different phases. A substance that appears to have color of the mother of pearl is known as the pearlite, and that's why its name is pearlite, because of this color only. An examination of pearlite at higher magnification reveals that it has a laminated structure, like I told you earlier that it is in the form of laminas or layers, and it is a composite and it consists of alternate layers of ferrite and cementite. So ferrite is Fe2O3 as was told in earlier lectures also, and cementite is Fe3C as per the chemical composition. At 0.8% carbon, almost total area consists of pearlite with a strength of around 850 Newton per millimeter square. So you can see that around the 0.8% carbon area, meaning the eutectoid point, it is mostly pearlite and it has a strength of 850 Newton per millimeter square. So cementite, we can see now, cementite provides the strength while ferrite retains the ductility of steel. So earlier also we have read how pure iron, it is very soft. So ferrite is very close to pure iron because the carbon percentage is very less in ferrite, whereas in cementite the carbon percentage has gone up and it is actually beyond 0.8% of carbon. So with the carbon increase, hardness increases but ductility goes down, but in ferrite due to the softness it is very ductile. At carbon content above 0.8%, the quantity of Fe3C begins to increase, as I told you now just now, and steel begins to lose its ductility. So this figure here is showing the relationship between pearlite and the carbon content. The carbon content is on the x-axis and the pearlite variation is on the y-axis. So you can see in the early portion of the curve, it is a linear thing, that is with the carbon content increase, the pearlite quantity is also increasing. So it goes up and up, and about 0.8% it is the highest, meaning the pearlite content is the highest. But further when we go beyond 0.8%, then we are seeing that the graph is coming down. It is because the cementite content is increasing instead of the pearlite now. So outside the region of the figure given here, within the range of carbon between 0.9 and 1.2%, pearlite structure still exists, but grains are surrounded by the cementite network. I told you just now that cementite increases beyond 0.8%, so the thing is happening here between 0.9 and 1.2%. We have pearlite here, but the cementite amount is increasing gradually. These cementite networks, not being parts of grains, are referred to as free cementite and are the cause of brittleness in steel. So the cementite actually will cause brittleness. Hardness is increasing, but at the same time it is getting brittle with increase in carbon content. So in general, the strength of steel does not increase due to the presence of free cementite. Later it may reduce below the level of 0.8% carbon steel. So we see that pearlite is an important constituent of steel. So its control becomes important if properties of steel are to be controlled. So pearlite actually is a combination of ferrite and cementite. So obviously its control is very much important because we will be getting different things with slight variations in that. There are three forms of iron in this figure given. So those are the alpha, gamma and delta. So alpha is the one which is up to about 900 degrees centigrade. Then gamma is the one which is up to about 1400 degrees centigrade, and beyond that from 1400 to 1539 degrees centigrade we get the gamma. So this transformation from BCC to FCC and further again to BCC keeps on happening depending upon the cooling rate and other things, carbon constituents, etc. During the cooling of pure iron, the transformation from gamma iron to alpha iron occurs at a unique temperature of 910 degrees centigrade. So like earlier you have studied that gamma iron is nothing but austenite and it is face centered cubic. So it changes to alpha iron, which is mostly ferrite, it is body centered cubic. So this change actually starts or occurs at a unique temperature which is 910 degrees centigrade. However, as carbon is added to the iron to form steel, this transformation takes place over a range of temperatures. So as we go on adding carbon to this, then the temperature range also changes. So the limits of this range are known as the critical points, and the higher temperature at which transformation starts during cooling is designated as A3, and the lower point where it finishes, the transformation finishes, is designated as A1. So in this figure you can see A3 and A1. So A3 starting point is around 910 degrees centigrade, and A3 can be in between 910 and 723, anything in between that, A3 can take up that value. But A1 remains fixed as 723 degrees centigrade. So this diagram is showing how gamma iron, that is austenite, is transformed into perlite. So again, coming back to the iron cooling diagram, it may be noted that carbon solubility is different in austenite than in ferrite. The FCC gamma iron can hold as much as 1.7% carbon in solution at 1130 degrees centigrade. So at 1130 degrees centigrade, the austenite can dissolve about 1.7% of carbon. Within the range of carbon under discussion, what we are discussing right now, the structure is entirely austenite at this temperature, and all the carbon is in solution. So only thing that is in this range, like from 900 you go to 1400 degree, so it is only austenite, and up to a carbon percentage of about 0.8%, not beyond that. So now we take up the carbon dissolving phenomena. The carbon is dissolved interstitially, or in other words, a carbon atom does not replace an iron atom to form part of the cube. So we know that the carbon atom, earlier we have discussed, it is smaller in size than the iron atom. So it is in the interstitial space. When the lattice is arranged to have a BCC structure, the carbon atoms are ejected from its site because the space is insufficient. So if this lattice, suppose it was FCC austenite and it changes to BCC, somewhat closer to ferrite, then what happens that the carbon which was in the interstitial space, like you can see in the figure A, it is ejected out because the space gets lesser. The FCC edge length is more than the edge length of the BCC. So this is the reaction which is taking place at A3. So that means at the higher temperature from which the transformation began, 910 degrees centigrade. So again, coming back to the diagram of the transformation of which consists of the A3 and the A1 temperatures, we can see here. So when this cooling starts and the carbon percentage is changing, when we see the 910 degrees centigrade temperature, so the curve is coming down, it is following a line, a dotted line is there in the figure, and it comes to the point of 0.8% carbon, and finally the lines A1 and A3 coincide with each other. So the BCC ferrite grains nucleate at the boundaries of the austenite grains. So this transformation is happening like this. We are now studying the microstructure changes. So in the figure you can see this is gamma austenite only, the circle, and only gamma is present inside. But as the transformation takes place, the ferrite is also coming in. You can see there are hatched lines inside in the second figure. So that is BCC. So now it's a mixture of both gamma as well as alpha. As the temperature reduces, the ferrite covers more and more space in austenite grain, which reduces in size. Separation of ferrite from austenite will result in rejection of carbon, which will be absorbed by the remaining austenite. So carbon is being ejected out, but it is getting dissolved in austenite, because austenite has a greater capacity of dissolving it. Hence the remaining austenite actually gets richer in carbon, and until the amount of carbon reaches 0.8%, this goes on and it causes precipitation of layers of cementite in the austenite region. So the third figure you are seeing here, this one, alpha and gamma are there. Alpha is coming in, and the last figure, the amount of cementite is very large now. So the perlite is reduced. Thus the austenite transforms into perlite, consisting of layers of cementite and ferrite. So at 0.8% carbon, this is the situation. It mostly consists of perlite, and the perlite is nothing but a mixture of cementite and ferrite, and layers of cementite and ferrite are there, lamina. Transformation of austenite is similar to eutectic reaction. Like previously in the iron carbon diagram, we have studied about the eutectic point also, which was about 4.3% carbon. So the transformation is similar to that, but here it is occurring in the solid state. At the eutectoid point, it is occurring in the solid state, so that's why the name is eutectoid. This eutectoid reaction or breaking of the solid phase austenite into ferrite and cementite takes place at temperature of 723 degrees centigrade, which is termed as A1, which was given in the figure. For this reason, perlite is also often referred as eutectoid. So in the martensite structure, what can be seen is that carbon atoms cannot move fast through the lattice between temperatures of A3 and A1. So like in the previous figure, I showed you the A1 and A3 temperatures. So between these, the carbon atoms do not move very fast. The formation of perlite and ferrite depends upon allowing sufficient time for the movement of carbon atoms. So when we want perlite and ferrite actually, so sufficient time is required for the movement of these carbon atoms. Then only we can get perlite and ferrite. So final conclusion is coming to what? That if it's a very fast cooling rate or transformation is very fast, then we won't be getting perlite and ferrite. So that means that such transformation is possible only under equilibrium condition. And the reason behind that is that the edge of the FCC cell is 23% greater than that of the BCC cell. And FCC is there in case of the austenite and BCC in case of the ferrite. So if a carbon atom is trapped between two iron atoms, they are kept apart and are not able to take up the position in the BCC cell. So what happens due to that? So the carbon atoms in martensite occupy the position on edge of any unit cell between two iron atoms, and due to this reason, the one of the edges on which this carbon atom is there, it elongates, and so there is distortion. So the net effect is that it is not at all now a cubic structure. So here we can see some figures where the structures of austenite, ferrite and martensite are given. So the first one is the austenite. It is FCC, where the carbon atom is in the faces of all the sides, so it is face centered cubic. The second one is the ferrite, which is nearby to BCC, body centered cubic. And the third one is not even body centered cubic, that is martensite, because the carbon atom is in one edge of the pattern, and in another edge it may not be there, so it causes distortion in the edge in which it is there, and in the other edge it is not there, so no distortion. So completely, if you see the structure, it is distorted. It is somewhat tetragonal and no longer cubic. So what are the effects of martensite production? Now we will see in the coming lecture. It may be emphasized that such distortions resulting into regions of high strain energy would impede the movement of dislocations. So there are certain dislocations inside the atomic structure, so their movement is impeded because of this high strain energy regions. So what happens that the material would lose its ductility and the hardness will increase. This trapping of carbon atom between the atoms of iron occurs when the steel is not allowed to cool in equilibrium condition, or in other words, it is suddenly cooled from the A3 to room temperature or to about 300 degrees centigrade. So like I told you earlier, if the cooling rate is very high, then this transformation or the neck formation of the TTT diagram is not crossed and it suddenly comes to martensite. So that's what is happening here, that if we are cooling from A3 was 910 degrees centigrade, suddenly to about 300 degrees centigrade, then only martensite will be formed. So this process of sudden cooling from A3 is called quenching, which may be achieved by plunging a heated steel A3 temperature into water or some other quenching medium. During this process, the carbon does not have sufficient time to diffuse. Hence, a quench treatment in which temperature is suddenly dropped from 910, that is A3 line shown in the figure previously, to 300 degrees centigrade, that is sufficient enough to create permanent hardening in steel. That's why martensite is quite hard. If the resulting structure is examined under microscope, it appears to be needle-like. So that is the structure of martensite. It is needle-like and it is often referred to as acicular. This is the name, acicular, of martensite. Now we shall see the effect of carbon content and critical cooling rate on the martensite hardness. So now we will be seeing only about the cooling rate inside martensite itself. Different kinds of martensite can also be there. So cooling rate only for martensite, not for others like perlite and other things. Different carbon contents in martensite will naturally result in different hardness. So at low carbon levels there is very little change in hardness. So obviously if within the martensite, if the carbon level is less, then it will be a lesser hardened martensite. The noticeable change in hardness is achieved when carbon content is at least 0.4%. So if it is about 0.4% carbon content, then we can see an increase in hardness or change in hardness. And it reaches a maximum, this hardness reaches a maximum at the eutectoid composition of 0.8%. Again, at the eutectoid point, the martensite will be the hardest one, 0.8% carbon. So the hardness that can be achieved through martensite transformation at 0.4 and 0.8% carbon are respectively 255 Wicker hardness number and 530 Wicker hardness number. So you can see the change from 0.4 to 0.8, it is a drastic change, how the hardness is increased. So the formation of martensite depends upon the cooling rate. As the carbon content increases, the critical cooling rate becomes slower. It means that it is easier to harden a steel containing 0.8% carbon than the one containing 0.4% carbon. Quenching in water results in fastest cooling rate and corresponds to critical cooling rate for 0.35% carbon, but this is not good for hardening because the carbon content is lesser here. Like in the figure also you can see how with larger carbon content the hardness can be increased in an easier manner, meaning the steel with higher carbon content is easier to harden. So in this session or lecture we saw the time temperature transformation diagram, how it is very important to determine the formation of perlite and ferrite and cementite, and further we also studied about the martensite. If the cooling rate is very high, then the time transformation diagram neck is skipped and we get the martensite. So all these things we discussed in this session and further we will discuss in the upcoming sessions. Thank you very much.